this class seriously. This is just an introduction to Holland's talk that will come next. And so this is a basic introduction to, and reminder maybe, to, I don't know, concepts, techniques of in algebraic topology. I will not say much, and I hope you will all be bored. So this means that you are well prepared for Roman's class. So let me start by the notion of a simplicial complex. Let me start by the notion of an abstract simplicial complex. So if X is a set, V is a set, that is known by P fin V, all the finite sets inside V. This is a subset of power set consisting only of power sets, and an abstract simplicial complex is an ideal in respect to inclusion. Although, so this is a subset of this one. Ideal means if maybe S inside. So if A is in S, B is in A, I'm defining what an ideal is. Then B is in S. And elements of which are called faces or synthesis. And such that, or which, let's assume, contains all the singletons. Which we call vertices. This is not new to anyone, I hope. Did anyone not see this definition before? Good. And most of the time we realize such a thing. We have a realization, logical realization of such a thing. So this associated with this S, we will have a topological space, which I will denote S, absolute value one, which is, well, basically to each such a guy, this A, the face in S is some, I don't know, a set of size n, or maybe size n plus 1. I want to think of it as an n simplex. And simply says are glued along common subsymmetries or subfaces. To globally picture this, let me put everything inside the probability measures on V, which are finally supported. So this will be new such that the support of mu must be finite and inside S. So along with each subset of S, of order, say, n+1, I will take all probability measures supporting on that subset. So this is an attachment to any vertex. 1, 2, 3 vertices. I will attach a weight. Probability measure is a weight, so I can think of it as an element in the simplex generated by abstract simplex generated by these 3 vertices. And if the coefficients, the weights of each vertex is positive, I'll get an interior point. Otherwise, I will get something like in a subsimplex, which is an S again. That's an idea. But this is just organization as a set. So how do we topologize this? We topologize, or S is topologized, that is, becomes a topological space, topologized, what is the direct limit topology. I'll explain, but let me briefly say in human language before. So if S was finite to begin with, then all this, I mean, I have finitely many cells here which I glue together, and there's one basically way to topologize it or to embed it into the big enough Rn as a sub-simplex maybe of the standard simplex, right? I mean, if V was finite, then probe V is topologized. I mean, canonically, you have compact topology on it, and this is a subset. Period. And if V is infinite, then I can view my set as I can exhaust it with finite subsets, finite simplification complex, and I will take the finest topology I could take such that all those embeddings of finite sub-simplification complexes are closed embeddings. Okay. So whenever you have a space and maps from many topological spaces into it, I can take the direct limit topology, which means the best, the strongest topology I can take, such that all those embedding, all those maps are indeed continuous. So let me just write down what I said now. So I guess I want to think of this maybe as a set to begin with, but then it will give me the topology as well as this is S prime in S finite. This is just a short annotation to what I just said. This equation, as I said, makes sense without the absolute value signs, makes sense with the absolute value signs. And once I have this equality as sets, this one I can topologize naturally with respect to direct limit topology, as I just explained. And this is the definition of topology here. What else I want to say?
Do you want to look strange? Do you want to take maybe finite subsets of V? Not of.
Yeah, okay. I know.
No, you're right.
Just,
I'm confused about your notation.
Yeah. Yeah. Full right to be. Okay. It's what I said. Ignore the formula. And now I will discuss the notion of a simplicial. So if you want this guy here, absolute value is a functor for simplicial complexes, the topological spaces, right? And so, given a topological space, I might ask, is that guy in the image or not of my simplicial complex? If it is, and I identify it with such, then I do have a simplicial structure on this topological space. This is a fancy name to more familiar notion of a triangulation. Is a homo. So given x here, given x, can I identify it with the guy s? So if I can, I think of this as well, maybe another realization of this guy, of the abstract simplicial complexes. And of course, topological spaces, which are simplicial complexes, are nice. We understand them combinatorially, and this is very helpful. So the point of view, or the basic point of view of topology is say, hey, we have a topological space X, we want to understand it, let's put a topological structure on it, combinatorial structure on it, and try to figure out what's up. This is way below your needs. Now, so if you have a ordering on a face index, assuming I'm having a simplicial complex S, and I do have a face in it, I can order the elements, the vertices consisting of this Z, 1, 2, 3, and this will give me a map from the standard 1, 2, 3 simplex called the 2. This sits inside S. This is the standard one sitting inside R3. The convex R of T1 into inside R3. So this is in one-to-one correspondence with a fine map from simplicial maps from standard simplices to S. So picking an element in S, ordering it, is the same. While having it, I can uniquely define an order preserving, a fine map from the standard simplex to this one, and vice versa. So this is an equivalence of sets. And we defined Cn of S to be the Freire-Wien rule. On such, for each presentation we want to think this or that. So most of the time, thinking combinatorially, we think of this presentation, but if we want to move to more sophisticated versions, like which I will discuss in a minute, like singular homology, I want to think of this in these terms. Now, there is a natural map, the natural maps delta I from this one to this one. And this one given just like restricting this to this will be delta restrict to the face which is opposite to a given vertex I. And identify this canonically with
This is delta on such what? Or antagonistic free abelian group on such what orderings or simplest
on well each such order. For different case. So I have this, I guess n plus 1 ordering for faces, for n faces. So our understanding that an n face is a face of size n plus 1, right? So I have this, we have these guys, and I define actually d from Cn to Cn minus 1, and dn by taking alternating sums with the i's. All these are very standard, and so fact, which is easy to check, if you do dn and then maybe if you do dn and then compose it with dn minus 1, if you go one step further, you get 0. You get cancellation of the sign change here. So what we truly get is a complex in the algebraic sense. For which we can take the homology. Standard thing, we take maybe at this place, I will define Hn of S to be the kernel of the n modulo the image of the n plus 1, which is inside it. So without yet discussing what it means, this is something I can do.
You should probably say something about how an ordering on a simplex gives you an ordering on the face. A shift.
I said that, I mean, given a face, if you order it, you will get a map from the standard simplex.
Di, is it a map from an ordered simplex?
Yeah,
To
the maps
Cn
are
minus
from the
1.
standard simplex, which is an ordered one. I have
To
bunch
an
of
ordered simplex which lives in Cn minus 1. So an ordering should.
oh yeah, sorry, yes, I should have said something.
You
Yeah.
should say about shifting.
Yes, so of course, when I got this restriction map, the blue guy here, from 1-3 to well, I guess that if we take this point of view, there is nothing I should say. So in the or maybe. Or maybe I guess I did say it here. That this is.
So this is the shift of all indices. Which
I choose when I identify that phase, the 1-3 phase of delta 2 with the standard simplex, the 1-2 simplex. Delta 1, I choose it so that 1 goes to 1 and 3 goes to 2.
Just restrict the order.
Which is just restriction of the order. And there's a.
There's no
By
shift or
natural
something.
numbers, so it's a shift now. For all indices
But the
which are
order you
greater
can see
than
it
9.
just as an abstract thing. Complete order.
What is an order? Is it by elements from 1 to n, or is it just an abstract order? Sorry, it's just, it makes certain
So
difference.
I guess that I didn't specify it. When I write it down, when I wrote it down, I meant by elements of 1 to n. But
Because it will further give a certain difference.
if you want, maybe I should have said
It's a blend of
you
the thing.
choose an isomorphism type of linear order on vertices.
Alright. No, it's not that I'm an idiot, it just
No,
it leads to certain differences.
Yeah, okay, but
It won't follow,
I
so
guess
it's
that what
just,
you missed.
Sorry.
I'm taking this as kind of a long reminder of things that people should
Alright.
know. So I'm trying not to fall into the little traps, and I trust you to help me with this. So what they want to say. Okay, so the next thing, which I already started discussing, and if we change this such distribution map here, will make a lot of sense, is singular homology. So if X is topological space, I can define now this gigantic object, which I will call Cn sin X. This will be the free abelian group. Sorry?
CNCX. It's a sentence in English.
Okay. Makes no sense anymore. So this free abelian group generated by, instead of taking simplicial maps here, let's take all possible continuous maps. From the standard n simplex to X. And I will define dn, or maybe the di's, in a very similar way. Combinatorically, just the same. To Cn minus. And I will get a similar simplex here. Maybe and I could get a complex of abelian groups. Take it to homologies, and get by definition H and the singular homology of X. And one of the first theorems that are proven in the post-logic topology is, or maybe before stating the theorem, let me observe that there is this natural map from simplicial maps, all simplicial maps, are continuous maps. So I have this natural map, and actually it's a ladder between these two syntheses that we see here. So all the horizontal maps I'm describing here are the two complexes, and I have ladder of maps here. So
Is there any reasons that S limiting these absolute values?
yes, I mean the singular homology was defined for an abstract simplicial complex. I mean, I can think of it. Usually we do think of it as something defined for the realization. We're identifying the two in mind, right? But a priori this is defined for the abstract simplicial complex. and now you can take the absolute value. You can realize you take it as topological space and take the singular homology of that topological space, and you have a natural map between the two, and this gives, and of course the natural map between the two complexes are indeed homomorphism of complexes, and they induce natural map between the homologies. So I'm give an isomorphism in homology. So I do get natural map from this guy to that guy for every n for very general reasons. The theorem is this is an isomorphism. So, the nice thing about it is a singular homology is a general machinery. I can define it everywhere. It's nicely behaved. It does not depend on whatever simplicial structure I put on a space, which in some sense it is a matter of choice and it is unnatural. Many spaces are given to me as, I don't know, manifolds or whatever, and are not bound with a favorite simplicial structure. So, and I do want to consider this natural invariant, which is the singular homology, and people think of the simplicial homology many times as a way of computing. Okay? Now, here's some sad news. Not every topological manifold is pre-unrealizable. Even if you care for nice spaces, for example, topological manifolds, not always you can put simplicial structure on this. So there is a point in somehow extending our world. So we are seeking now for still some combinatorial theory in order to, we want to understand topological spaces. We are seeking for combinatorial theory as simplicial spaces, simplicial complexes, but which is kind of richer. So this brings me to the next topic, which is CW complexes. So who saw this in class? Not all. Okay, so I'm wasting your time, but I'm doing something meaningful for you. So let me define this. So CW complex is a topological space with, or maybe again, I can think about it in some sort of an abstract way, but usually I will mix the two things, which are one as a CW complex is given by the following. I'm giving you a construction recipe. Sets Sn. So the Sn will be the set of n cells in the guy, and maps to be specified. From spheres to okay, just a minute. And are constructed inductively. So I'm constructing now a space X. I will start with x0, which will just be this is just points, vertices. And now, so this identification actually I think of as a map from S0 to X0. And now assume we had constructed xn minus 1. Xn minus 1, we construct xn as follows. We are given, so this is part of the data which I did not specify. So for every s inside Sn, a map. So this guy Sn represents a ball. And I'm giving a map from Sn minus 1, which is the boundary of ball. So Dn here. Closed ball. To xn minus 1. Now I want some condition on this, but let me maybe find something. Let's hold this for 1 minute. And we find so xn will be what we had before, xn minus 1, and we add for each element of S we add such a ball, and we glue them together, we glue the new. So this you should think again as a set of indices. This is a set of indices. So we have such many balls, and I'm doing these balls to the smaller skeleton I already have, a smaller layer, using these maps from the boundaries of the ball to that thing. So equivalence relation. So a point x in and S. The S ball is equivalent to this.
Fortunately, I don't know if people know about push-on topological spaces. I find it nicer with the push-on diagram.
Right. So so you want to write, I don't know, -1.
What is this?
Sorry?
What is S in Xn?
What is the push out? You want to write here xn times n?
Well, actually on the other side.
I'm not sure now.
Okay, but I have a more serious correction. That was just a comment, but there's one thing that's not quite correct. I mean, usually, if you define a CW complex, the sets Sn and the specific ways you do that are not part of the data. So the CW complex is just a space for filtration, x0, x1, x2, x3, such that xn somehow arises from xn minus 1 by gluing certain spaces to it, like a dick. but somehow the data is just the space with its filtration, and
yes.
not the
Okay,
other stuff.
I would say so far I didn't sort of I wrote a recipe for constructing a space without specifying a definition yet, and actually I didn't even I didn't even finish doing that because, well, I said that I will specify some maps. These are these map phi that I said here. Also, I said that I will say some. They should satisfy some conditions, which I haven't yet. In order to say the conditions, and again, this is not the definition yet. So, in order to say what the conditions are, I guess I want to first say that this definition of we can inductively topologize the guys xn accordingly. So we take the cost topology here, and we take, I guess, on this guy, we take the direct limit topology. So there is a natural way to topologize this thing, and we do so, and doing so, we may then in retrospect insist that all these maps, which I had to specify when I constructed xn, but there are maps to xn minus 1, and insist that the maps of Phi will be continuous. Moreover, there is another technical requirement, and the image Vs of Sn minus 1 will meet only finitely many smaller cells. And cells are the images of the board in this construction. So, and now I want to repeat what Roman said. You are unhappy.
Yes, very happy. Can I give the definition like I would?
Yes. I mean,
If you don't mind.
no, I am happy about it.
But it's okay. Let's break it down. Okay. Sorry, but just this definition. So I would define homological space. Okay, maybe house down. X in a CW with a filtration. And so we have filtration of subspaces. The union of everything is the X. Is a CW complex. If the following holds, so, or maybe to make it formally correct, let's introduce X then, minus 1. If two conditions hold, first of all, how does Xn arise from Xn minus 1? Well, it does it in the following way. So you call it the index as Sn. Maybe let me call it En because we have Sn in the spheres. So if you have for every n such a push out, and people familiar with push outs of spaces? So it has a universal property. And it just means that xn arises from xn minus 1 by gluing a bunch of disks along attaching maps of the boundary. So it's the same thing.
And what is IN in your What is
I
IN?
understand, but I
IN is xn, is the index set. But somehow the data is just a filtration, and you just claim that this must exist for every n. And the second thing is the topology, and this is only important if you have infinite filtration. So it has a co-limit topology, so a set is closed if this is closed for every n.
Do you assume some finiteness for each fixed n?
That's all. And then maps of CW complexes are just topological maps that respect the filtration. And then it's automatic that you only hit finitely many cells if you
What is the motivation for what you get?
So, do you want to answer?
motivation for introducing this notion?
Yes.
Well, it's still nice. It's still a space that's built out of simple things, disks that you glue together. But it's much more flexible than a simplicial complex, which is also nice. It's also built from triangles that you glue together. But it's more flexible. So, for example, if you have a topological map between two CW complexes, this topological map is always homotopic to a map of CW complexes. You can always homotope it such that the filtrations are preserved. If you have a topological map between realizations of simplicial complexes, it's not homotopic to a simplicial map. You have to subdivide the domain simplicial complex. Then it is, but somehow it's less flexible. You have to subdivide if you replace by simplicial maps and so on. So this is somehow like a good compromise between flexibility and still having a nice space built out of simple things.
Thanks. So, maybe just I want to emphasize what.
Another question to Roman, but some kind of countable base or something you assume, or both or not?
I wouldn't.
No?
No.
No. No, I just want to know
What about the finiteness that you said before?
which
You can have uncountably many cells.
So I just repeat this, which is indeed important. I didn't mind saying it actually. That a CW complex is a space with that filtration, and then the existence of this structure is part of the definition, but not the particular one.
But the filtration is a part.
The filtration is a problem. The thing is somehow there is something called the cellular homology and the cellular chain complex, and it's defined just in terms of the filtration. And somehow when people compute the cellular homology, then there's always this issue of choosing orientations of cells, but this is just choosing the push-outs. But somehow the cellular chain complex exists, it's like it's there. And choosing and doing orientations is just finding a basis of this complex. So because sometimes it's confusing what are actually orientations, what is this business? It's just choosing the push-outs.
But
So,
say a circle with just two vertices on it and to one cells will for you be different from as the same circle but with one vertex and one.
That's a different CW structure, yeah. But if I put in these orientations that I do when I compute homology, this is just the same CW complex, but I choose different push-outs.
So I wanted to say something without actually defining about cellular homology. Feel free to replace me at the very end of this talk. I don't know what is the time now.
5 minutes.
Oh. Okay, so I actually say very little. To compute homology, so associated with such CW complex, I can indeed attach a homology, which is defined by means of the cells and by means of, I mean, well, given a particular choice of such representation, I will define to each cell a generator of some chain complex Cn. So maybe I'll just say the following. A complex. Oops. Of constructed with the ion or Sn as generators to Cn for which the homology coincides with a similar homology. Of X. So as with the previous theorem that we've seen for simplicial complexes, I can have this combinatorial version of the homology and it computes the same thing. Same here. Only here I didn't define what the boundary map between the SNs are, but the CNs are, and well, I don't have the time to go into it, but many times it is enough to say something just by this fact. For example, spheres, like Sn. So I have here 1, 0, 7. And 1 S, and I'm gluing the boundary to that point. So this would be my x0, this would be my xn, and that's it. So if you believe this statement without actually specifying the boundary map, you can see that the homology of the sphere, either way, you can see that the homology of the sphere must be Z at 0 and n, and 0 as an s. And I guess I don't have really the time. I want to discuss some more examples, but I promised to Roman to say something about classifying spaces and how much time maybe we have? Okay, you will have to do it yourself then. So, so we meet again after lunch, or if you